Some of the most important skeletal muscles in the human body are the muscles that make up the shoulders, also known as the deltoids. The deltoid muscle, also known as the common shoulder muscle, due to it being present in many animals, forms the rounded contour of the shoulder. It is made up of 3 different muscle fibers, being the anterior or clavicular part, the intermediate or acromial part, and the posterior or scapular part. These are also known as the front, side, and rear delts, respectively. The deltoids make up most of the shoulder and give them their rounded look when they grow. The deltoids form a type of triangle shape. The base connects to the upper part of your scapula, or shoulder blades, and to the side of your clavicle, or collarbone. The point of the deltoids connects to the side of your humerus, the arm bone between the shoulder and the elbow. The function of the deltoids is primarily to help move your arms in different directions, front, side, and backwards, as well as protecting and stabilizing your shoulder joints, which are very fragile. Deltoids are used in many activities, such as swinging, pulling, pushing, and lifting. The deltoids also help compensate for a lack of strength in the rotator cuff. The 3 different parts of your deltoids each contribute to different movements. The anterior deltoid does shoulder flexion, or lifting the arm forwards. The intermediate deltoid does shoulder abduction, which is lifting the arm sideways. And the posterior deltoid does shoulder extension, or pulling the arm backwards. The deltoid muscle is part of a third-class lever system, with the effort being located between the fulcrum and the load, creating a mechanical advantage of less than 1. This results in a large range of motion, but a lot of required force to move. The fulcrum is the shoulder joint. The effort is the force exerted by the deltoid muscle at its insertion on the humerus, and the load is the weight of the arm, plus any additional resistance that comes from any objects that are held. Torque for it is created by multiplying the force of the applied force and the moment of the arm, where the moment of the arm is the perpendicular distance from the axis of rotation, the shoulder joint, to the line of action of force. The deltoid applies force at an angle to the humerus, generating torque. If the moment of the arm is longer, like when the arm is extended, more torque is needed to lift the arm. The deltoid is strongest when the arm is at about 90 degrees of abduction, as the arm is the longest.
The sport we chose which involves deltoids is tennis. Specifically, the deltoid is very important to the tennis serve. As the force is applied using a third-class lever, the force causes a rotation rather than a translational movement. Therefore, it would be better to use torque, or rotational force, than the traditional force. Torque is calculated using T is equal to radius times force, and this is vector multiplication, so angle matters. To calculate work, simply multiply the torque applied by the change in angle. W is equal to torque times delta theta. For the same reasons we use torque instead of force, kinematics should be done with angular values rather than the standard velocity, acceleration, and delta x. Theta, W, angular velocity, and alpha, angular acceleration, should be used in their place. Now you see a video of me swinging my tennis racket, and one thing you'll notice is that the position of the load relative to the effort changes quite a lot, where at some point it's almost directly over the effort or even behind it maybe, whereas at others it is way far down the arm, and that greatly changes the mechanical advantage throughout the swing. So that is something that has to be taken into account if you were to do actual calculations involving torque and the deltoids. So that is a potential issue. Here is an example situation. A lot of this has to be approximated as, for instance, as I said earlier, the load position changes with time as the arm extends, and the weight is also an estimate, as it's hard to find data on the weight of your arm, and that had to be estimated, and the weight of the tennis racket had to be estimated. But using this data, for example, we know that the approximate force / effort position is about 12 centimeters away from the fulcrum. You can calculate torque if you actually could find the force, which is something that we could not do in this circumstance. And same with the load. Approximately, let's say 24 centimeters out on average, and so you could again calculate the weight, which we approximate to be 4.3 kilograms times gravity, 9.81 meters per second squared, and get the torque due to gravity and the weight of the arm plus the tennis racket. So, although we did not do an example with specific measurements, this is an example of how you could get those measurements. To actually find an accurate measurement of torque throughout the swing and work would require, I believe, calculus, as values are changing constantly and there's no constant acceleration. It probably varies as the load moves and due to other factors. Here is another example problem. This time we're using actual numbers. This is not for my tennis swing. This is for the swing of a pro tennis player. A couple assumptions were made that are not entirely accurate, but will be reasonable enough for this circumstance. First was that the swing is perfectly circular, which it may not be. And so we said that a professional tennis player should easily be able to swing around 100 miles per hour or 45 meters per second. We approximated the arm length plus racket length, a professional tennis player, to be about 1.3 meters. Another important thing to take into consideration is that we have not accounted for other possible sources of velocity. For example, a tennis player will use their hips to rotate their entire body as they go up to hit the tennis ball, and that could contribute to some of the velocity of the ball, as well as the upward velocity driven by your knees extending upwards. Now for the problems. First, we converted from 100 miles per hour into meters per second, which we got 45 meters per second, as that is the standard SI units. But as we were dealing with an angular kinematics problem, we then had to calculate from linear velocity into angular velocity, and we calculated that to be about 35 radians per second. From there, we used our first equation to find the approximate angular velocity, and we got 429 radians per second squared. Then we used that angular acceleration to find our approximate time for the swing. And for that, we got 0.08 seconds approximately, which is very fast. To show just how quick that is, I have here a looping video of a tennis player's actual swing. You can see how quickly he gets up and hits the ball after getting into that ready position, and just how fast he hits that ball. I believe the world record is somewhere around 140 miles per hour, but these pros can easily hit 120 miles per hour. So our time was actually an overestimation of a tennis player's swing.
Thanks for watching, guys. This is Xavier.
And Nathan. This has been a classic Mr. P Lab video, and I'll see you soon.
Don't forget to smash that like and subscribe.
And hit that bell hard as you can. Peace.